All right, so let's finish this week. Just a reminder that we will have a midterm number 1 on Monday, October 25th. So it's not this Monday, but it's the next one. It will cover lectures from the beginning until today's lecture. So until we finish the material for today. So whether I finish it today or maybe I'll have to spend a few minutes on Monday, we'll see. And homework number between 1 and 3. We do it this way that you have the midterm a week later so that you'll have a chance all of next week to ask questions during your discussion sections in office hours. Make sure that you get that homework number 3 correct, and so that you'll have time to study. As I said in my announcements, it is open book, open note. You will be allowed to access your notes, the textbook, whether they're written or digital. It's not going to be proctored. But I do recommend that you spend time studying, because if you don't study, you will not have time to finish. It's about 30 questions, and it will be timed. You have 1 hour to finish them during lecture, so from 4 to 5. And so at the very minimum, you should know where you can find the information. You should have a map in your head or in notes if you want to write, so if I ask something about fusion, do you know where to go to look it up? But I definitely recommend studying. So, all right, so I think I'm going to go on. Homework 3 will be posted this evening, so you can start working on that, and then you'll have a chance to go over it next week in your discussion section, and then have your quiz number 3. All right, so let's go back to what we were talking about, which is the sun. And we talked last time about the competing forces in the sun, how there's a competition between gas pressure, which pushes out gravity, which is trying to compress everything. This gravity compresses the gas, makes its temperature go very high, to the point where all the plasma, all the particles that make up the plasma are moving so fast that sometimes they run into each other, and the strong force takes over. And even though they're protons and they naturally try to go away from each other, the strong force, if they come close enough, the strong force will bind them together. And through a series of reactions, which we didn't cover in this class, but through a series of reactions, you will go from hydrogen to the next heaviest element, which is helium. So the sun is transforming hydrogen into helium in its belly, right? What we call the core. And out of this, energy is being produced at a huge rate. That energy is carried out in the form of photons, which are the particles of light. And they carry this energy through what is called the radiative zone. And that's where we ended last time. As they try to leave the photons, they get bounced around like crazy, because everything, there's all these charged particles, right? Particles with some electrostatic charge. And the photons interact with them, and so their path gets bounced around until, after about 1 million years, they get through the entire radiative zone, and they get into this part, which is called convection zone. Here, the energy, instead of being transported by photons that are bounced around, it is transported, it's the heat basically that is transported by hot gas that rises up to the surface of the sun. So convection is something that we are all very familiar with, because if we've ever boiled water, we see convection. This is when there is a difference in temperature between the bottom and the top of either a gas or a liquid, like in the case of water. So the heat source heats the bottom of, in this case, the pot. So the gas or the water in this case gets heated, Because it's hotter and because it's hotter, it rises to the surface. When it gets to the surface, because the surface is cooler, it cools off, and as it gets colder, it sinks back down to the bottom of the pot, and then it becomes a cycle, right? And we see it here in the boiling pot. So this is really water, cells of water or parcels of water that are getting heated up, and then they rise to the surface, they cool off, and they sink again. We call this process convection. It's convecting, right? It's going up and down. It's hotter, less dense material rises to the surface, it cools off, and it sinks down again. Same thing happens with air in a room. For example, if you have a fireplace going, the hot air of the room will go up to the top, and then if it can cool off, it'll fall again and then rise again. So it is like a cycle. That's right. In the same way that a convection oven works. I actually don't know how a convection oven works, so I'll have to look that up. But I imagine that's why it's called convection oven. It probably has a difference in temperature between the top and the bottom, and that's probably how it works. But I'll have to look it up. In the sun, the same thing happens. In the sun, let me go back to the previous slide. So here, you remember, as you go further into the sun, it gets hotter and hotter. So the radiative zone is very hot compared to the surface of the sun, right? In the surface of the sun, what's above? Well, it's basically space, right? And it's a lot cooler. So heat can escape on the surface of the sun. So gas will get heated, by the radiative zone. And as it gets hotter, it goes up to the surface. When it gets to the surface, it cools off and it sinks back down. And in fact, so this is simulating or illustrating the sun, where the hot gas goes up, it gets to the surface, and it sinks back down. And just like a pot of water looks like it's bubbling, the same thing happens on the sun, like on the surface of the sun, where it looks like bubbles. And in fact, this is an actual movie taken from one particular spot in the sun. So you can actually see how it is bubbling, and it's not water. In this case, it is hydrogen mostly, and other elements, as we learned before, but mostly hydrogen gas. That is, it's hot, it gets to the surface, it cools off, and it goes down again. The places where you see the bubbles, where it's brighter, where it's lighter, that's where it's hotter. And then as it cools down, like it is in this figure here, so as the gas gets cooler, it goes back down on those dark edges. That's where, it sinks back down, it gets hotter again, it goes up, and so on. So it is doing this cycle. Yeah. Now, I've been saying the word surface a lot, and really what I mean by that, it's not a surface that you could walk on, right? That is all gas. So what I mean by surface is what we see, right? When we look at the sun, how far deep into the sun can we see, And that's what we call the surface of the sun's surface, right? In quotations. So photosphere is this part, like if you look out the window and you can see the sun, that part that you see, that's what we call the photosphere. Photospheres, in reality, what it is the layer where photons, visible photons, right? The photons that you can see, can finally travel unimpeded. As I mentioned before, in the radiation zone, they get bounced around. If we were able to go inside the radiation zone, of course we would die. But if we were able to send a camera inside, we wouldn't be able to see anything, because photons, which carry light, right, which carry images, get bounced around so much, you would not, you would it's like you would see the light that is right next to the camera, right next to the camera. But you wouldn't be able to see beyond that because photons are being bounced around. And then in the radiation zone, things are going up and down and up and down. And finally, you get to the photosphere, and then the photons are able to travel freely, finally. And so that's why those photons from the photosphere are able to come to us, and then we can see them. So that's what we call the photosphere. Now, if we had X-ray vision, or if we had infrared vision, which we'll talk about the different parts of light, then the photosphere would look different. It would be maybe slightly deeper in or slightly outer from that. So we call the photosphere the part that we see with our eyes, right? In visible light, so light that you can see with your eyes. The temperature of the sun here drops dramatically, right? I mean, we started at 15 million Kelvin, and by the time you get to the surface of the sun, it is about, by the way, this symbol, I was asked by a student, this symbol means approximately. So it's like a wiggle. It means approximately 6,000 Kelvin. A little more precise is 5,800 Kelvin, but it's approximately 6,000. Do I want you to remember any of these numbers? Yes, please remember that the center of the sun is higher than 10 million Kelvin, and that the surface of the sun is about 6,000 Kelvin. Again, it's going to be an open book test, so if I were to ask this, you would be able to look it up. I don't want you using hard drive or memory space remembering little numbers. I'd rather you learn concepts. Can I repeat the temperatures? Yeah, the center of the sun is 15 million Kelvin. All I want you to remember is that it's more than 10 million Kelvin, which is where you can have fusion. And the surface of the sun is about 6,000 Kelvin. Another question, could I repeat? Okay. The photons are exhausted by the time they leave. Yeah, the core is, the very center of the core is 15 million Kelvin, right? It changes. So the core is anywhere where the temperature is more than 10 million Kelvin. That's right. Are there any hotter objects in the universe? Many, but we will get to that. So stars have different temperatures depending on how massive they are, and that'll be the subject of a whole other lecture. All right, after the photosphere, there is something called the chromosphere. We're actually not going to talk about this. You'll find it on your textbook. They tell you things about it, but for the purposes of what we're learning, it's not very important. So the chromosphere is, it's like an atmosphere. So the sun has an interior, which is everything from the photosphere inside. So it's core, radiative zone, convection zone, and then there's the photosphere. And then outside of that, there's the chromosphere. So it's photosphere, chromosphere, and the corona. And again, we're not gonna, you can read about it if you're interested, but we're not gonna say anything about the chromosphere. But after the chromosphere, something happens, which used to be a big mystery, and they've actually figured this out in the last 10, 20 years, which is that the temperature was going down, 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 down as you go out from the center. And then all of a sudden, the temperature goes way back up, right? So we were down to 6,000 Kelvin, and then all of a sudden it goes up to like 1 million or 2 million degrees Kelvin. And like I said, it used to be a mystery, but now we understand that that it is energy that is being injected into this very thin gas, and that raises the temperature by magnetic fields, which will be the next subject. So we'll get to magnetic fields in a little bit. For now, all I want you to know is that there is an outer part of the sun, which is called the corona, that has a very high temperature and where gas is at an extremely low density, right? The density of the sun, of the gas, of the plasma gets lower and lower as we go out from the center. By the time we get to the photosphere, it's pretty low and it keeps going down, 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 right? It's thinner and thinner, but then the temperature goes up and that place is called the corona. We can see the corona with our naked eye only when we have a total eclipse. This is a picture taken from the eclipse that happened 4 years ago here that was visible from the States. And it's this very thin gas that is like a halo around the sun. So a corona is this very thin gas, so it looks like this, and not to be confused with this, right, which has been in the news for the last 18 months or a little longer than that. But it's the same idea. Corona, for those of you who have a Spanish background, you know that it means crown. And it's the idea that it's this crown that, I mean, in the case of the virus, it's the crown around the virus. In the case of the sun, it's this crown that is around the sun that we can see. All right. So actually, I have a couple of questions. Let me just address them. So bigger stars are actually hotter. We will get to that again in a couple of weeks. And another question is, do you need to know, you don't need to know anything about the chromosphere for the purposes of this class. Just because if you remember, the goal of this class is to get into all the violent stuff. So I'm only trying to teach you the things that you need to understand in order to understand the violent phenomena in the universe. The chromosphere doesn't really play a role in this. And so that's why we don't learn about the chromosphere, but you can read about it in your textbook. And then I have the question of whether you should memorize the placement of each layer of the sun. Yes, you should know that the core, I mean, and it makes sense, right? Like maybe you don't need to memorize it. So in terms of the core, the radiation zone, and the convection zone, if you think about it, you don't need to memorize it because the core, if you know what the core is, well, that's where it's hottest. So as long as you know that it goes from hotter to less hot, then it makes sense that the core would be in the center. The next zone, the radiation zone, why can't photons go, in a straight line? Because it's so hot and everything is moving so fast. So it has to be pretty close to the center. And then the next zone, you know that it's a convection zone, that the hot gas goes to the surface, right? So you know that it has to be the one that is next to the surface. And then as long as you remember that the photosphere is the surface of the sun, then there you go. You've basically memorized all the layers. So, all right, so the solar corona, like I said, it's the outermost layer of the sun, and it's extremely hot, and it has a temperature that is more than 1 million degrees Kelvin. And like I said, this is a mystery that has been solved in the last 20 years or so. And we now know that it is heated by magnetic fields, which I'll talk about in a few slides. So again, just like it happened in the center of the sun, atoms lose electrons. So the gas becomes a collection of protons, electrons, and other nuclei. We call that plasma. So the corona, the solar corona, is this plasma that is super thin and very hot. And the problem with it being so hot is that, remember, in a gas or in a plasma, when it is very hot, the individual particles move very fast. And if they move very, very fast, they may reach what is called the escape velocity, meaning the velocity that is necessary to escape. And then they might leave. And in fact, that is what happens. A lot of this gas ends up being too hot for the sun's gravity to keep it. And remember when we were talking about how planets form, I mentioned that it's kind of hard to hold on to gas. You need a lot of gravity to hold on to gas. And the problem with this gas, it's so thin and it's so far from the center of the sun, and it's so moving, the individual particles are moving so fast that a lot of it ends up leaving the sun very fast. And so how do we observe this? We observe this as the solar wind. So this is what I've been talking about when I was talking about the comets, right? I kept talking about this solar wind. So we finally get the explanation of what the solar wind is. It's basically very, very hot plasma, right? Which is charged particles that are above the surface of the sun. And they're so hot that they end up flowing. They end up moving beyond the sun. And so it is a flow of charged particles from the surface of the sun, and it goes throughout the entire solar system. And we've been able to observe it even beyond the planets. It just keeps going. What happens when the solar wind comes close to Earth? We will talk about that next time, actually. We won't quite get to that right now. All right, so this was...
I have a question.
Yep.
So you mean the solar corona even hotter than the radiation zone because it is 1 million Kelvin degree?
Yeah, so the core of the sun is 10 million Kelvin. So part of the radiation zone is above 1 million Kelvin, right? So it keeps decreasing throughout the radiation zone. So the radiative zone, so the radiative or radiation zone, you know, this one here is above 1 million Kelvin. So no, the corona is not hotter than the radiative zone. The corona is hotter than the convection zone, and it is hotter than the photosphere. That's correct.
Okay, thank you.
Is the core of the sun 15 million Kelvin or 10 million Kelvin? Both. I mean, the center of the core is 15 million Kelvin. As you go out from the center, it drops, right, to 14 million, 13 million, 10 million, I mean, 12, 11, 10 million. Once it goes beyond or below 10 million Kelvin, fusion can't happen anymore. So then we don't call it the core. Just everyone, please keep that in mind. It's the hottest at the center. And as you go out from the center, the temperature is going to drop, you know, slowly or little by little. Did I say the radiation zone is hotter than the solar corona? Yes, I did say that. All right. Yeah, I don't want to get you confused with, is it 15, is it 10? I want you to have the concept, the idea that it is very hot in the center, incredibly hot, so hot that there can be fusion. And fusion happens above 10 million Kelvin. Maybe I shouldn't have told you to memorize numbers. But I don't know, I guess I want you to have some concept of how hot it is. And, you need a very, very high temperature in order to have hydrogen fusion. It is 10 million Kelvin. It is even hotter in the center, but it doesn't matter if it's hotter, you can still have hydrogen fusion. You know, the hotter, the better, the hotter, the easier it is to fuse. But once you go out from the center, then the temperature drops. And so you cannot have fusion anymore. And then we don't call it the core. These pictures sometimes are a little bit confusing, right? Like the one that I'm showing, because they show the core one color and the radiative zone a different color. And then you get it in your head that they're very distinct zones or layers, and that's not the case. I mean, it all looks the same. The only thing that is changing is the temperature. And we call it the core simply because there is fusion in that part of the sun. All right. Okay, so does fusion happen in the core? Yes. Okay, I guess I answer your question. Okay, sunspots, we'll get to that. Is the radiation zone the hottest out of all the layers? No, the core is the hottest of all the layers. All right. Okay, great. This is a good question. Is the wind, the solar wind, is it like the wind that we feel on Earth? No, it is the same in that it's also gas that is in motion, right? The gas that we feel on Earth is molecules of like air in the atmosphere that are in motion. They're flowing from one place to another, and we can feel it like touching us. The solar wind is also plasma in motion, but it's a lot thinner. It's the density is much lower, and it is charged, whereas the air here on Earth is not charged, it's neutral. Sometimes it is charged, and that's why your hair gets all like woo. So anyways, but the point is, with the solar wind, if you were to stick your hand out of your spaceship, I don't think you would feel it the way that you feel this wind here, because it's a lot thinner, right? The density is much lower. But in terms of it being flowing material, yes, it is the same. And I will get to sunspots soon. And okay. All right, so we've gone through the anatomy of the sun, or at least the part that we need for the next topic. And we're finally ready to start talking about the violent phenomena that happen in the sun. All right. All right, so we get to the part about the furious sun and about the explosive stuff that happens in the sun. Everything that we're going to talk about from here to the end of the topic has to do with magnetic fields. So magnetic fields, let me just remind you, right? Or let me just introduce you a little bit to the concept of magnetic fields. Everyone who has, not everyone who has, sorry, most of us have played with magnets at one point or another, whether it is, because we own something that has magnets, and I have a magnet right here, which of course you can't see because of my background. So I'm going to have to come down from space again and get into my boring background. There you go. So now you can see that I have a magnet right here. And magnets, you're used to the idea that they have two poles, usually a north and a south pole. And when you look at them, you don't see anything around them, but there is something around them that is called a magnetic field. And you're used to magnets. And actually, let me stop sharing for a second. So, if I bring my paper clips from the last class, you're used to the idea that magnets attract things that are metallic. But maybe you're not so used to the idea of a magnetic field, which is the part around the magnet, which is capable of attracting metallic things. Also, you may not be familiar with the idea that magnets are able to interact with charged particles, which we've been talking about that in the sun. You have all these charged particles, which are able to interact with magnets. You don't see a magnetic field with your eyes because you can't. I mean, they're not visible. You usually need something like like iron dust or iron filings in order to see the magnetic field. So hopefully you can see this as I approach, as I put the magnet, there you go, close, how do I angle this? There you go. So as this is harder than I thought. As I put the magnet close to this iron dust, so this is metallic dust, right? It interacts with the magnet, and you can see that it's not random how it lines itself up. It actually lines, let's see, let's get it closer to the camera. There. You can see that it forms some pretty nice lines, right? Nice lines that go straight up and down, and then they curve around. And the reason they curve around is because they're trying to follow those invisible magnetic field lines. If I put the magnet in the center here, you will be able to see, let me move it around. This is so much easier to do when I'm in the classroom, because you guys would be able to play with this. I would pass it around. But hopefully you can see that the lines are going around and going to the other side of the magnet. And as I close this, and I get the metallic dust all around, notice, I mean, it may be really hard to see in the camera, and with the reflection, I try to, hopefully you can see that, but there's basically small thin lines that go all the way from the top to the bottom on both sides. So let me share my screen again. And you can do it at home if you have a magnet and you have compasses. You will see how they follow the magnetic field lines, these invisible lines that connect the North Pole to the South Pole of a magnet. And they're very thin and they go all the way around. So what happens is that the sun is like a giant magnet. And, oh, let me go back to the sun. No, that's not what I meant to do. Let me fly back to the sun so that I look cool again. All right, so the sun is like this giant magnet, and it has a pole. It has a North Pole and a South Pole. The reason why the sun has a magnetic field is because of all these charged particles that I was telling you about. When you rotate charged particles, which the sun is rotating, magnetic fields appear. And so that's what's happening in the sun. It's not, remember, the sun is not a solid, it's a gas, and it's fluid. And so it is not a very well organized magnetic field, but it roughly has a North Pole and it roughly has a South Pole, and it has a million, or I don't know how many, but many, 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 many lines, magnetic field lines coming from the top, from one pole to another pole. You can't see this with your eyes. You need to see, well, I mean, if you had like a metal dust, right? And you could sprinkle it around the sun, you could see those lines, but of course it would probably melt. So instead, you can actually see these lines with those charged particles, the plasma. When it interacts with the sun, you are actually able to see those lines. But let me not get ahead of myself. I will get to that in a minute. The thing that you need to know is that the sun is very messy because, again, it's made of gas, and this is true for every star, not just the sun. But there is all kinds of motions within the sun. One, there is convection. I already told you about that. So then you get huge amounts of gas that is going up and down and up and down. And remember, these there's a lot of charged particles that are doing this near the surface of the sun. In addition, the sun rotates in a way that is very different from the Earth. The Earth just rotates all at once. The sun, being a gas, is able to rotate at different speeds. And in fact, the equator rotates faster than the poles. So if you were to look at a region in the sun's equator, so by equator, I mean like the dividing line in the middle, right? It takes only 25 days for the equator to rotate once around. But as you go up from that, as you go to the poles, it takes longer. It takes, you know, all the way to the North Pole, it takes 35 days. This is what we call differential rotation. The different parts of the sun rotate at different speeds. And, you know, so you can imagine how it starts off being all nicely lined up when it comes to the magnetic fields. But as it starts rotating at different rates, those magnetic field lines are going to start getting tangled. So imagine you have the sun, it starts up with nice straight magnetic field lines, and then the equator is rotating faster. So as it's rotating faster, it gets all tangled. And I should have brought a rubber band, but you try it at home, right? Or with the cable from my computer. So you know that if you have a cable and you start to rotate it at, you know, in opposite directions, it's going to start developing kinks, right? This parts of the cable where, you know, it forms loops, and then it gets all tangled. And I think hopefully you can see that in your screen. So if you do that with a rubber band, it's even cooler, right? Like you start rotating the rubber band and then it gets all tangled, and it forms these loops, it forms these kinks, and it gets all messy. So that's what happens in the sun. The sun, between those two things, between the differential rotation and the convection near the surface of the sun, the magnetic field lines get all messy. That has a very important effect. So what happens is some of these kinks, some of those magnetic field lines, which again are invisible and you cannot touch them, but they're very real, right? Like the ones that I was showing in my box here. Some of them will come up through the surface of the sun and you know, back down. So some of these kinks will break through the surface of the sun. The problem with that is that you have convection near the surface of the sun. That's why I needed to talk to you about the convection zone. Near the convection, I mean, if one of these invisible magnetic field lines goes through the surface of the sun and it happens to go through where the gas is going up and down, what it does is that it will stop the convection at those parts, right? Again, we cannot touch a magnetic field line. I don't feel the magnetic field lines of this magnet, but they're very real. I don't feel them, but the iron dust feels it. In the same way, I don't feel the magnetic field lines of the sun, but the plasma and the gas of the sun, they can feel them. And in the case of convection, it stops convection. So let me ask you, what happens if convection is stopped? So let me give you a poll, and I'll launch one of these generic polls. So the question is, there's only 3 answers, but A, B, and C. So if convection cannot bring fresh material to a region, to a certain region of the solar surface, on the solar surface, what happens to the temperature of that region? So let me launch this. Question is, if convection cannot bring fresh material to a region on the solar surface, what happens to the temperature of that region? Answer A, it gets hotter. Answer B, it stays the same. Answer C, it gets cooler. So if convection cannot bring material, if it's stopped, if you stop convection in a region of the sun, what happens to the temperature of the region in that part of the solar surface? Does it get hotter? That's A. Does it get cooler? That's C. Or does it stay the same? And that's B. All right, so most people have answered. The answer is correctly. You answer C. The majority said answer C. It gets cooler. Let me explain why, just in case it's not clear. Solar surface is at 6,000 Kelvin, right? That's why I'm giving you the numbers, because it's at 6,000 Kelvin, the radiative zone is much hotter. It's in the millions of kelvins. So the gas, you know, because of convection, goes down, it gets hotter. In fact, let me, yeah. So it goes down, it gets hotter, and then it goes up and it heats up the surface of the sun. If you stop this, if you make this convection stop, then hot material cannot go to the surface. Let me show you, like, if you guys have seen this lava lamps, it's the same, exact same principle. You have a heat source in the bottom, which is just a light bulb, right? That's all it is. And then you get these blobs of colored material. As they get heated up, they rise to the surface, and then as they get cool again, they sink back down. So if the equivalent of putting a magnetic field line there would be, you would stop, you would keep it, you know, the green material wants to come up to the top, but it can't because, sorry, I just realized I didn't stop the poll, sorry. Okay, so anyways, if you had a magnetic field line that stopped this convection, you would end up, the green stuff would not be able to get to the top. So then the top wouldn't look green. What we're simulating with this is the green stuff is the hot gas. It wouldn't be able to come up to the surface. And so the surface of the sun would get a little cooler. What does that look like? What does it look like if a region of the sun is a little bit cooler? It looks like a sunspot. So somebody asked me, what are sunspots? That's exactly what it is. They are regions in the visible surface of the sun, or in the photosphere, where the temperature is a little cooler because convection is being impeded by a magnetic field, line. So it's still very hot, right? And I don't want you to memorize these temperatures. I just want you to know that it gets a little cooler. 4,500 Kelvin is still very hot, but it is cooler than the rest of the surface, right? By more than 1,000 degrees. So when you look at the sun, it actually looks darker. The regions where it is colder or cooler looks darker than the rest of it. And in a couple of lectures, we're going to learn that the hotter an object is, the brighter it looks. That's a physics thing, right? But so the sun is all bright because it's hot, the surface. And if there are some regions that look darker, it means that they are cooler. And what causes that? Magnetic field lines that have gotten tangled, and then they go through the surface and they mess with convection, and so they create cooler spots. Right. So there's an animation of what that looks like. You get a magnetic field line that is going through the surface of the sun, the visible surface, the photosphere, and then, you know, it gets darker, and so you see sunspots. Some question that a lot of students ask is, so do you always get sunspots as pairs, as two? Very often you will see two, but even in this video, you can see how it's a little messy, right? Like maybe one of the magnetic field lines is coming a little bit separate from the other, so you end up getting three instead, or you might get like a little cluster. Sometimes they're so close, you only see one, and so on. So it's not always pairs like that. A lot of the times you only see one. In this same video, you saw that magnetic field loop going through the surface. So again, think about it as being the dust, the metal dust, right? Following that arch, that loop. You can't see anything, sorry. If not worth it. So if you, instead of the iron filings, if you get some plasma, some gas that is going, it starts climbing up from the sunspots and it goes through the loop, then you're able to see this arch, and you can actually see it with a telescope, or yeah, with a small telescope, you can actually see these loops. And so they are huge arching columns of gas, glowing gas that is a little bit cooler, and they can extend for tens of thousands of miles above the surface of the sun. This is a relatively slow process as the gas climbs up and it goes, you know, from one side to the other. And they may glow for hours or days, and sometimes they glow for even weeks. They do eventually go away, you know, because the sun is very dynamic. It is constantly changing and moving. And so, you know, they will eventually go away. They go away after days or weeks. Here's a video taking, as this is a real video, from a spacecraft that is observing the sun. And you can see them, I mean, if you look at the time, this is in fast motion, right? So over here is time in hours, but you can see how it takes a few hours for it to form. Then it forms this huge arch, and then eventually it goes back down. So they are huge, right? I mean, they look small compared to the sun, to the size of the sun, but they're huge. That's compared to the approximate size of Earth. You could fit many Earths inside one of these prominences. Let me, I know that it's getting late, but I really want to get through this. So give me 2 more minutes and I'll let you go. So sunspots have been tracked for centuries, because this is something that you can see with a small telescope. You can see with even binoculars, right? But don't ever point binoculars at the sun, please. You have to have filters, otherwise you ruin your eyes. But you know, people have been doing this for centuries, that they look at the sun and they see whether there are spots or not, sunspots or not. Even without binoculars, even without the telescope, you can actually see them, but you just have to have the right filters, please. So people have been tracking them for centuries. Like I said, we have a very good record of how many sunspots you see on average per day since 1750. And you will see from this that it seems to be a periodic thing. It's not regular. Sometimes you get times when you see hundreds of sunspots in one day. And sometimes it's not quite as crazy, it's not quite as much, but it is something that it is periodic. And what scientists have been able to determine, anyone who observes this, is that every time that we have a peak period when there are more sunspots, that corresponds to a solar maximum, meaning when you get a lot of violent phenomena on the surface of the sun. And we're not going to have time to get to the very violent phenomena, but we'll get to that on Monday. Solar minimum, it corresponds to times when you don't see the sunspots. And this seems to be on a cyclical pattern. And that cycle is, on average, 11 years. So about every 11 years, you get to a peak where you see a lot of activity in the sun, a lot of sunspots, and then it goes back down. Sometimes it's 12 years, sometimes it's 10, it's not exactly 11, but it seems to be a very periodic time. So next Monday, we'll start with why do we get this periodic thing? And then what happens in the sun, right? Like what violent phenomena happens because of this. So have a good weekend. I'll stay behind for questions, and we'll finish this on Monday. All right, so let me stop recording. Have a good weekend, everyone.